Oh, so we're doing cosines
Okay,
today,
so
too?
it's essential to be able to identify the opposite pairs of parts in the triangle below. Identify the opposite part to the part listed.
She said part.
So which side would be opposite from angle E? Remind me? Side DF. All right. Which side would be opposite from angle D? Side EF. And then finally, which side would be opposite from angle F?
DE.
DE is correct. Okay. So here's what we're doing today. Today we're going to learn about what's called the law of sines and law of cosines. Up until now, sine and cosine were only used with right triangles. Well, it turns out if we're a little bit sneaky about how we put the formulas together, we can actually use sine and cosine for any kind of triangle. But it has to be derived from using it strictly with right triangles. So I'm going to show you how those are derived with the law of sines. We're not going to have time to derive it for the law of cosines. I actually just told you what the law of cosines is, and it's listed below down here. But we're going to derive the law of sines, so you can see that it's actually a formula that comes from right triangles, and then we can be tricky about how we maneuver it and use it with non-right triangles. But the essential piece of information that you need to pull from a picture today is opposite pairs of parts. So when I talk about an opposite pair of parts, it's just like what we just did. An angle and the side opposite from it. We need to be able to identify those pairs because that tells you which of the two formulas to use. If you have a complete opposite pair, you use law of sines. If you don't have a complete opposite pair to work with, then that's when you use law of cosines. And that's the only way you can really determine which one to use. All right, so what we're going to do is turn this triangle ABC, and notice the lowercase letter markings. They're marked by what's opposite from them. In other words, here's angle A, and opposite from angle A, we call that side little a. Of course, we could call that side BC also, but that lowercase a is saying that's the side across from A. So that's where the lowercase letters are coming from. All right, I want to turn this triangle into two right triangles. What can I put in the picture to make that happen? Hello? What can I put in that picture to make that happen?
A line.
Yeah, what kind of line?
Straight line.
A perpendicular line, also known as an altitude. You got it. Very good. So if you put it in an altitude, and I just chose to draw it there. I could have drawn it from B to side B, from angle C to side C. I could have done it any of those three ways. I just chose to do it from A to little a. All right, now this is the law of sines, so I want to set up some sine ratios. Turns out I can set up two sine ratios having drawn in this altitude and create two right triangles. Well, I could set up more than that, but I'm going to set up two sine ratios. The first one I want to know is what is the sine of angle B? So what is the ratio for the sine of angle B? Who knows that? Sine is what again? The ratio is what over what?
Oh,
Opposite over hypotenuse. Okay, so what is opposite from angle B? Oh, there's nothing there. That's why you can't tell me. Let's put a little D on that altitude. Sorry about that.
yeah.
Okay, so opposite from angle B is what leg? D, little d. And what's the hypotenuse in that triangle? C. Good. Okay, so opposite was D, and then the hypotenuse right there is C. All right, what is the sine ratio for angle C? What is it? D over B. Yeah, opposite from angle C is D, and then the hypotenuse of that triangle is B. Okay. That's a capital C, but in the first one, that's a lowercase c, because the lowercase are referring to the sides, so the ratio has the sides in it. And then the thing with the degree mark, that's referring to an angle, so that's a capital letter. Capital letter is angle, lowercase letter is sides.
Can I just put like an angle thing by?
No. Do it just how it is. Okay, now, we want one formula. This is obviously two different equations. So I need to find a way to combine these into one formula. I also want to only include things that are contained, that are sides or angles in the original triangle. So what's in those two equations that's not in the original triangle? D. It's not a side length in the original triangle. So I want to somehow get rid of D, and I want to somehow combine those two equations. Any ideas? No. Good idea.
Set them equal.
We want to be able to set two things equal to each other. What did both of those equations have? D. So let's rearrange both of them and set them equal to D to begin with. So if I want to set the first equation equal to D, I must have multiplied both sides of the equation by little c. So D is equal to little c times the sine of angle B. And if I rearrange the second equation to be D equals, I must have multiplied both sides by what? The little b, yeah. So B times the sine of angle C. All right, now that I have them both set equal to D, I can set them equal to each other using substitution. In other words, I can take this D out and substitute it with B times the sine of C because those values are equal. So I have B times the sine of angle C. That's equal to little c times the sine of B. That's the law of sines, guys. That's a formula showing how the parts of a non-right triangle fit together. The thing is, we usually don't leave it looking like that. We usually write it as a proportion so that we have the A's with the A's, the B's with the B's, and the C's with the C's. How could I get B, little b, over to the other side? Yeah, if I divide both sides by little b. Now it's over here. What about C? Same thing, divide both sides. Now it looks a lot more like what you would see if you looked up the law of sines. What about A? A kind of feels left out of this whole thing. Do you think that the sine of angle C over C equals the sine of angle A over A? So why don't we have any A's in this equation right here? It just so happened to be that's the way I picked to draw the altitude. But if I had drawn the altitude from C to C instead, A would have been involved in this whole thing and we would have found the same pattern with angle A and side A. So the law of sines says that the sine of angle A compared to the side across from it, little a, is equal to the sine of angle B compared to the side opposite, that's little b, and that's also equal to the sine of angle C compared to the side opposite from it, little c. And of course, you would only use two of these ratios at a time to make one equation. So if you had a problem that involved the b's and the c's, then I would just have these two things right here involved. How many of those 4 variables would I have to know to be able to solve this equation? What? 3. Any 3 would do. Like if I knew this number and I knew this number and I knew this number, then I could solve for what? Angle C, right?
Angles.
If I knew this, then I could solve for side C. That's the one I don't know, side C. Right. Either way, you have to have one complete ratio of measurements. I need to know either both angle A and side A, or both angle B and side B, or both angle C and side C to be able to use the law of sines. If you don't have one complete ratio, there's no way you could know 3 values. So that's pretty much your key there. If you have a complete ratio of sides, you use law of sines. Okay, if we don't have one complete ratio, then that has us relying on what's called the law of cosines. Take a look at the law of cosines down here. So you'll notice that each version of the law of cosines, that looks a lot like what? It starts to look a lot like the Pythagorean theorem. But we know Pythagorean theorem only works for right triangles, so actually this amount right here takes care of the difference in length between non-right triangles and right triangles. It kind of is the adjustment of the formula when you have a non-right triangle. Okay, so the law of cosines only involves one angle at a time. So let's say we use the first version. It's because we're involving angle A in the problem somehow. You'll look in the very front of the formula and you see that the side across from angle A is involved also. It's in the front of the formula. Then side B and C fill in the rest of the formula. Right? If I'm using law of cosines to solve for something involving angle C, then I would use this version of the formula. C in the front and C at the end, so it bookends the formula. And then this time the A's and the B's fill in the rest of the formula. So the one opposite pair of parts that's involved in the problem bookends the problem, and then the other two sides fill in the rest of the formula. And this is going to make a lot more sense once we start actually working through the problems. That just probably looks like a lot of letters and numbers stuck together right now. It'll make sense in a few moments when we start using it. All right, but here's what you need to remember when you want to decide which one of the formulas to use. If you have the measures of a complete pair of opposite parts, then you use the law of sines. If you do not have the measures of a complete pair of opposite parts, then you use the law of cosines. So that basically needs to be your first question that you ask yourself when you're trying to work one of these problems. All right, next video are the practice problems.